In this video, I'm going to take you through the 6.1a lesson. I might not work through all the problems, but the key will have all of them worked out on Google Classroom. Number 1 says, find the area of the following shapes. On the grid, a horizontal or vertical segment joining the two dots has a length of 1, meaning that each of these squares is 1 square unit. We're not going to show all of the area formulas for these because they're just triangles, rectangles, or squares. And I think there's two strategies. I will label the areas, although I'm not going to show the work for each shape. One strategy is you break up the inside of the shape into shapes you then can find the area of. So this is a 3 by 2 rectangle, which means it has an area of 6. This is an area of 1. This is a triangle that has a base and height of 1. So 1 times a half is a half. And this would also be a half, which means that the total area for this would be 8 square units. For B, using a similar process, we can either break up the inside, but another strategy that can be equally helpful, and on this one, on B, either technique would work, but I could also go around the shape and say that this is a 1, 2, 3 by 1, 2, 3 square, which means it has an area of 9, and then subtract away the 4 triangles that are right triangles that look to all be congruent. And these right triangles have a base and height of 1 and 2, which means the area of each one of these is 1. So that means that the area left over in the middle is 5 square units. For C, same idea. I now understand kind of the two options, either break up the inside or go around the outside. You definitely want to try to break it up, though, into larger chunks and not into all of the little pieces. So this is a rectangle with area of 2. And I also have a 1, 2, 3, 4 by 4 square, so it has an area of 16. Take away, this is a half, plus this is 2 times 1 times a half. This has an area of 1, plus that one also has an area of 1, and this one has an area of a half, plus 2, which is 16 minus 3 plus 2, which means the area is 15. Doesn't matter your strategy. Like I said, I'm not going to show all the area formulas for these because the shapes are somewhat basic, but I would label and track these so that your total area is not off by 1 square unit in either direction. Number 2, we're going to look at creating a square and also looking at the slope. So the slope of line segment AB is down 1 and right 1, 2, 3, 4. So it means it has a slope that is negative 1/4. Which means that if I want to construct a square, then the adjacent side should be perpendicular, which means that it should have opposite reciprocal slope. So I'm going to make this for AD. So I know D is going to be somewhere up here. And so that would mean it has a slope of 4. That's the opposite reciprocal of negative 1/4. So I'm going to go up 1, 2, 3, 4, and right 1. So that's in fact D. And that would mean then across from AD would be BC. 1, 2, 3, 4, right 1. And there's C. And then DC should have a slope of negative 1/4, down 1, right 1, 2, 3, 4. So this was negative 1/4, this was 4, and that was 4. And so we can see how we can build a square by using opposite reciprocal slopes. And on number 3, we are going to then build some squares, and they give us the area. So it might be easiest to start with the one that has an area of 9. We can build these in any manner. It must be a square. It can't be a rectangle. And it must land on a dot. So the 3 by 3 gets me my area, which is 9. So that means this side is 3. An area of 2 is not as easy to do, nor is 18. I would encourage you to pause the video and see if you can figure these out without just copying from what I'm going to draw, but if you do need a hint for one of them, you could watch one and pause it after that and try the other one. But for an area of 2, what we can do is use the strategy from problem number 2 and have a rotated square. And so there is my answer, and the outer part is 4 minus 1, 2, 3, 4. It's a total of 2, which is 2. So that tells me that this inner part does have an area of 2 square units. And that would mean this side length is the inverse operation of squaring, which is square rooting. And that would mean that the side, this diagonal side, is root 2 units. And 18 is going to be a similar strategy of having a square embedded in a square, and you don't always get this first attempt, so you have to kind of do trial and error. And you can either subtract the outer ones or focus on finding the area of the inner one, but that's really the square that has the area that I'm after. Let's see if I can actually erase this. And I'll focus on maybe breaking up the inside just to change it up. So this would be 3 times 3 times a half would be 4.5 is each one of these, which gets me my total area, which is 18 square units. So if it is, essentially we've realized that if it is not a perfect square, this is a perfect square, we're going to have to alter it and turn it on its side somehow. So there's that one and this one. On the next page, you're welcome to pause this, but I'm just going to kind of read through these. So we notice that 9 then can be represented by using vertical line segments because 9 is a perfect square. What we notice about 2 and 18, those are not perfect squares in that there is not a number squared that will give us 2 or 18. And so therefore the sides have to be diagonals. And in fact, the square root of these numbers is not nice, and that's what Module 6 is about. So a perfect square is a whole number that is squared. So our perfect squares would be 1, which is 1 squared, 4, 9, 16, 25, 36, 49, etc. Those are our whole numbers squared that get us our perfect squares. To find the area of a square given the side length of the square, we square the side length, which is essentially derived from length times width, but those two dimensions are equal in a square. To find the side length of a square given the area, we are going to square root the area. We are also reminded what we figured out in Module 5, which is square and square roots undo one another. Let's take a look at the table. So I'll fill out some of these. I'll let you try a couple of these and check them with the key. So if we have an area of 1, we know 1 times 1 will get us 1, so that would mean the side length is 1. If the side length is 2, then 2 times 2, the area would be 4. If the area is 3, well, that's not going to work out nice, so we will just write square root of 3. If each side is square root 13, well, square root 13 times square root 13 is 13. You can also check that by kind of working from the area back down to the side length. 20 would be 400. X would be square root of x. Y would be y squared. And 16x squared would be 4x. 4x times 4x is 16x squared based on what we learned in Mod 5. Down here we are assuming on a lot of these that since we don't have a large knowledge base of square roots that these are going to come out nice. So if you don't know what some of these are, you can trial and error these, but 625 is a perfect square, it's 25. 2500, well, it almost looks like 25, so I'm guessing that 50 will work. And 50 times 50 with the extra zeros is 2500. This one looks like 81, which means that if I make it 9 and I place a decimal point, maybe with some extra zeros, so 0.09 times 0.09 would be 81, move the decimal place 4 places, so that one would check out. And variables are a little bit trickier. For variables, a to some power times a to some power is going to give me a to the 4th. Based on what we learned in the last module, this would be a squared. So a squared times a squared is a to the 4th, just like 25 times 25 is 625. And then b to some power times b to some power is b to the 2nd, and that would be b. The rest of these you will see in Google Classroom as well as 17 and 18, and we'll probably talk about these last couple on Tuesday.